In statistics, maximum likelihood estimation is a method of estimating the parameters of a statistical model given data. The method of maximum likelihood corresponds to many well-known estimation methods in statistics. For example, one may be interested in the heights of adult female penguins, but be unable to measure the height of every single penguin in a population due to cost or time constraints. Assuming that the heights are normally distributed with some unknown mean and variance, the mean and variance can be estimated with MLE while only knowing the heights of some sample of the overall population. MLE would accomplish this by taking the mean and variance as parameters, and finding particular parametric values that make the observed results the most probable given the model. In general, for a fixed set of data and underlying statistical model, the method of maximum likelihood selects the set of values of the model parameters that maximizes the likelihood function. Intuitively, this maximizes the agreement of the selected model with the observed data, and for discrete random variables it indeed maximizes the probability of the observed data under the resulting distribution. Maximum likelihood estimation gives a unified approach to estimation, which is well defined in the case of the normal distribution and many other problems. History. Maximum likelihood estimation was recommended, analyzed and vastly popularized by Ronald Fisher between 1912 and 1922. Reviews of the development of maximum likelihood have been provided by a number of authors. Some of the theory behind maximum likelihood estimation was developed for Bayesian statistics. Principles. Suppose there is a sample x1, x2, xn of n independent and identically distributed observations, coming from a distribution with an unknown probability density function f0. It is however surmised that the function f0 belongs to a certain family of distributions, f theta theta, called the parametric model, so that f0 equals f. The value θ0 is unknown and is referred to as the true value of the parameter vector. It is desirable to find an estimator which would be as close to the true value θ0 as possible. Either or both the observed variables xi and the parameter θ can be vectors. To use the method of maximum likelihood, one first specifies the joint density function for all observations. For an independent and identically distributed sample, this joint density function is now we look at this function from a different perspective by considering the observed values x1, x2, xn to be fixed parameters of this function, whereas θ will be the function's variable and allowed to vary freely. This function will be called the likelihood. Note that denotes a separation between the two input arguments and the observations. In practice it is often more convenient to work with the logarithm of the likelihood function, called the log likelihood, or the average log likelihood. The hat over indicates that it is akin to some estimator. Indeed, estimates the expected log likelihood of a single observation in the model. The method of maximum likelihood estimates θ0 by finding a value of θ that maximizes. This method of estimation defines a maximum likelihood estimator of θ0. If a maximum exists, an MLE estimate is the same regardless of whether we maximize the likelihood or the log likelihood function, since log is a strictly monotonically increasing function. For many models, a maximum likelihood estimator can be found as an explicit function of the observed data x1, xn. For many other models, however, no closed-form solution to the maximization problem is known or available, and an MLE has to be found numerically using optimization methods. For some problems, there may be multiple estimates that maximize the likelihood. For other problems, no maximum likelihood estimate exists. In the exposition above, it is assumed that the data are independent and identically distributed. The method can be applied however to a broader setting, as long as it is possible to write the joint density function f and its parameter theta has a finite dimension which does not depend on the sample size n. In a simpler extension, an allowance can be made for data heterogeneity, so that the joint density is equal to f1, f2, fn. Put another way, we are now assuming that each observation xi comes from a random variable that has its own distribution function phi. In the more complicated case of time series models, the independence assumption may have to be dropped as well. A maximum likelihood estimator coincides with the most probable Bayesian estimator given a uniform prior distribution on the parameters. Indeed, the maximum a posteriori estimate is the parameter theta that maximizes the probability of theta given the data, given by Bayes' theorem. Where is the prior distribution for the parameter theta, and where is the probability of the data averaged over all parameters? Since the denominator is independent of theta, the Bayesian estimator is obtained by maximizing with respect to theta. If we further assume that the prior is a uniform distribution, the Bayesian estimator is obtained by maximizing the likelihood function. Thus the Bayesian estimator coincides with the maximum likelihood estimator for a uniform prior distribution. Properties. A maximum likelihood estimator is an extremum estimator obtained by maximizing, as a function of theta, the objective function, this being the sample analog of the expected log likelihood, where this expectation is taken with respect to the true density. Maximum likelihood estimators have no optimum properties for finite samples, in the sense that other estimators may have greater concentration around the true parameter value. However, like other estimation methods, maximum likelihood estimation possesses a number of attractive limiting properties. As the sample size increases to infinity, sequences of maximum likelihood estimators have these properties. Consistency. The sequence of MLEs converges in probability to the value being estimated. Asymptotic normality. As the sample size increases, the distribution of the MLE tends to the Gaussian distribution with mean and covariance matrix equal to the inverse of the Fisher information matrix. Efficiency, i.e., it achieves the Krammer-Kutarau lower bound when the sample size tends to infinity. This means that no consistent estimator has lower asymptotic mean squared error than the MLE. Second-order efficiency after correction for bias. Consistency under the conditions outlined below. The maximum likelihood estimator is consistent. The consistency means that having a sufficiently large number of observations n, it is possible to find the value of theta 0 with arbitrary precision. In mathematical terms, this means that as n goes to infinity, the estimator converges in probability to its true value. Under slightly stronger conditions, the estimator converges almost surely to. To establish consistency, the following conditions are sufficient. Identification of the model. In other words, different parameter values theta correspond to different distributions within the model. If this condition did not hold, there would be some value theta 1 such that theta 0 and theta 1 generate an identical distribution of the observable data. Then we wouldn't be able to distinguish between these two parameters even with an infinite amount of data. These parameters would have been observationally equivalent. The identification condition is absolutely necessary for the ML estimator to be consistent. When this condition holds, the limiting likelihood function has unique global maximum at theta 0. Compactness. The parameter space theta of the model is compact. The identification condition establishes that the log likelihood has a unique global maximum. Compactness implies that the likelihood cannot approach the maximum value arbitrarily close at some other point. Compactness is only a sufficient condition and not a necessary condition. Compactness can be replaced by some other conditions, such as Both concavity of the log likelihood function and compactness of some upper-level sets of the log likelihood function, or existence of a compact neighborhood n of theta 0 such that outside of n the log likelihood function is less than the maximum by at least some epsilon greater than 0. Continuity. The function lane f is continuous in theta for almost all values of x. The continuity here can be replaced with a slightly weaker condition of upper semi-continuity, dominance. There exists d-integrable with respect to the distribution f such that, by the uniform law of large numbers, the dominance condition together with continuity establish the uniform convergence in probability of the log likelihood. The dominance condition can be employed in the case of I.D. observations. In the non-I.D. case, the uniform convergence in probability can be checked by showing that the sequence is stochastically equicontinuous. If one wants to demonstrate that the ML estimator converges to theta 0 almost surely, then a stronger condition of uniform convergence almost surely has to be imposed. Asymptotic normality. In a wide range of situations, maximum likelihood parameter estimates exhibit asymptotic normality, that is, they are equal to the true parameters plus a random error that is approximately normal, and the error's variance decays as 1n. For this property to hold, it is necessary that the estimator does not suffer from the following issues. Estimate on boundary. Sometimes the maximum likelihood estimate lies on the boundary of the set of possible parameters, or the likelihood gets larger and larger as the parameter approaches the boundary. Standard asymptotic theory needs the assumption that the true parameter value lies away from the boundary. If we have enough data, the maximum likelihood estimate will keep away from the boundary too. But with smaller samples, the estimate can lie on the boundary. In such cases, the asymptotic theory clearly does not give a practically useful approximation. Examples here would be variance component models, where each component of variance, sigma 2, must satisfy the constraint sigma 2 0. Data boundary parameter dependent. For the theory to apply in a simple way, the set of data values which has positive probability should not depend on the unknown parameter. A simple example where such parameter dependence does hold is the case of estimating theta from a set of independent identically distributed when the common distribution is uniform on the range. For estimation purposes, the relevant range of theta is such that theta cannot be less than the largest observation. Because the interval is not compact, there exists no maximum for the likelihood function. For any estimate of theta, there exists a greater estimate that also has greater likelihood. In contrast, the interval 0, theta, includes the endpoint theta and is compact, in which case the maximum likelihood estimator exists. However, in this case, the maximum likelihood estimator is biased. Asymptotically, this maximum likelihood estimator is not normally distributed. Nuisance parameters. For maximum likelihood estimations, a model may have a number of nuisance parameters. For the asymptotic behavior outline to hold, the number of nuisance parameters should not increase with the number of observations. A well-known example of this case is where observations occur as pairs, where the observations in each pair have a different mean but otherwise the observations are independent and normally distributed with a common variance. Here, for 2n observations, there are n plus 1 parameters. It is well known that the maximum likelihood estimate for the variance does not converge to the true value of the variance. Increasing information for the asymptotics to hold in cases where the assumption of independent identically distributed observations does not hold. A basic requirement is that the amount of information in the data increases indefinitely as the sample size increases. Such a requirement may not be met if either there is too much dependence in the data, or if new independent observations are subject to an increasing observation error. Some regularity conditions which ensure this behavior are: the first and second derivatives of the log likelihood function must be defined. The Fisher information matrix must not be zero, and must be continuous as a function of the parameter. The maximum likelihood estimator is consistent. Suppose that conditions for consistency of maximum likelihood estimator are satisfied, and θ0 interior, f greater than 0 and is twice continuously differentiable in θ in some neighborhood n of θ0. Sup θn, θf, dx less than infinity, and sup θn, θf, dx less than infinity. I equals e, θ lane f exists and is non-singular, e, sup θn, θ lane f, less than infinity. Then the maximum likelihood estimator has asymptotically normal distribution. Proof, skipping the technicalities since the log likelihood function is differentiable, and θ0 lies in the interior of the parameter set. In the maximum, the first-order condition will be satisfied. When the log likelihood is twice differentiable, this expression can be expanded into a Taylor series around the point θ equals θ0, where is some point intermediate between θ0 and. From this expression we can derive that here the expression in square brackets converges in probability to h equals e minus θ lane f by the law of large numbers. The continuous mapping theorem ensures that the inverse of this expression also converges in probability to h minus 1. The second sum, by the central limit theorem, converges in distribution to a multivariate normal with mean 0 and variance matrix equal to the Fisher information I. Thus, applying Slutsky's theorem to the whole expression, we obtain that finally, the information equality guarantees that when the model is correctly specified, matrix H will be equal to the Fisher information I, so that the variance expression simplifies to just I-1. Functional invariance. The maximum likelihood estimator selects the parameter value which gives the observed data the largest possible probability. If the parameter consists of a number of components, then we define their separate maximum likelihood estimators as the corresponding component of the MLE of the complete parameter. Consistent with this, if is the MLE for θ, and if G is any transformation of θ, then the MLE for alpha equals G, as by definition it maximizes the so-called profile likelihood. The MLE is also invariant with respect to certain transformations of the data. If Y equals G, where G is 1-to-1 and does not depend on the parameters to be estimated, then the density functions satisfy, and hence the likelihood functions for X and Y differ only by a factor that does not depend on the model parameters. For example, the MLE parameters of the log normal distribution are the same as those of the normal distribution fitted to the logarithm of the data. Higher order properties. The standard asymptotics tells that the maximum likelihood estimator is square root n consistent and asymptotically efficient, meaning that it reaches the Krammer-acute RL bound, where I is the Fisher information matrix. In particular, it means that the bias of the maximum likelihood estimator is equal to 0 up to the order n-1/2. However, when we consider the higher order terms in the expansion of the distribution of this estimator, it turns out that θ-MLE has bias of order n-1. This bias is equal to where Einstein's summation convention over the repeating indices has been adopted. IJK denotes the JKTH component of the inverse Fisher information matrix I-1. And using these formulas it is possible to estimate the second-order bias of the maximum likelihood estimator, and correct for that bias by subtracting it. This estimator is unbiased up to the terms of order n-1, and is called the bias-corrected maximum likelihood estimator. This bias-corrected estimator is second-order efficient, meaning that it has minimal mean-squared error among all second-order bias-corrected estimators, up to the terms of the order n-2. It is possible to continue this process, that is to derive the third-order bias correction term, and so on. However, as was shown by Carnot, the maximum likelihood estimator is not third-order efficient.